we will look at a few other optimizations that could fall in the category of hardware specific optimizations. These might not make obvious sense in the context of compilers. Sometimes it might, but usually it might not, but in the synthesis context it definitely does. We still haven't started with the actual synthesis tasks, which would be the scheduling, register allocation and so on, but this is still a pre-processing of the internal representation. But this keeps in mind the fact that the target is synthesis and not compilation. So, these are some of these transformations. Again, the extent to which we will study these individual transformations would be primarily to point out the intuition. We will not necessarily look at the detailed algorithm for doing so. Okay. Tree height reduction. The objective is to balance the data flow graph in some way wherever there is a choice. We have a data flow graph that might have been inferred in that fashion from the way the user wrote the code, and therefore, the representation looked like this, but you can see that we can transform that expression structure in some way, which would lead to that data flow graph changing its structure. What would be the advantage of doing so? The critical path, which would be defined as the length of the path from any of the inputs to any of the outputs. This is a data flow graph. So, there are no cycles here. So, there is a defined maximum path length, but in general the point of the balancing is to try and reduce the maximum height of the structure. That is what is called tree height reduction. Doing this transformation leads to a reduction in that length, maximum length or height from 3 down to 2. What is the advantage of doing so? Now, if I submit this transformed graph into scheduling, and if I have enough resources, then I can finish this faster. Essentially, I will need only 2 cycles if each operation takes only 1 cycle. What if I did not have 2 resources? If I had only 1 adder, then does the transformation make sense or not? It does not improve, but does it make it any worse? It also does not. So, we will say that we will go ahead and perform this anyway. But on the other hand, whether you should do it or not then depends on how many resources you have. We could still take the view that we will go ahead and do this anyway, it can't be worse, right. It can only be better, that depends on what resources you have later on. You could also make it dependent on the resources, but the whole point of considering this as a pre-processing step is that we want to decouple these phases to the extent possible. If we can avoid bringing in later stages, like the scheduling is certainly a later stage. If we can somehow assure ourselves that the transformation that we are making is at least no worse, will lead to no worse results for any of the subsequent passes, then it may be okay to go ahead with the transformation. Okay, so, that is a tree height reduction. The objective is to the extent possible balance the DFG. How do you do this? You have to achieve this through a sequence of rotations of these nodes, right. Even though here the example is simple enough, in the general case this has to be done through individual transform. You take each of the nodes and some rotation has to be performed. Essentially, something like this got transformed to something like this, right, and that caused a reduction in the overall height. So, we will not go into the algorithm for doing so, but just pointing out that such a possibility exists and it may improve the results of synthesis. One more, control flow to data flow refers to another kind of simplification that could be done on the CDFG, again with the objective of simplifying the final design. What we have here is an if statement. If there is a condition, then we are assigning something to y, otherwise we are assigning something else to y. What is the internal representation? This we had already seen, since there is an if statement that translates to that fork join structure in the IR. What is there in the fork join structure? Each of these nodes translate to a respective DFG of that basic block. So, y equals a plus b is this basic block, y equals a minus b is this basic block. Then I have that condition that also in the general case might have its own expression that may need ultimately to be merged with the prior basic block like we had seen earlier. But that is what the general CDFG structure looks like. And the most straightforward way to take it to the next level of synthesis is that you schedule one basic block at a time. So, that you have from an if statement like that, or let us this could in general be several clock cycles in length. And what would the overall strategy be? We schedule each of the, we schedule this basic block separately, this one separately, and so on. Each would lead to a partial finite state machine, right. If this was 3 states, then I would have a sequential FSM with 3 states. If this one was 4 states, then I would have an FSM that looked like that. A condition here, if that condition check is performed in one cycle, would look like that. So, we are building the FSM along with doing the schedule, and the simplest way is each basic block you schedule separately, and maybe you have a structure like that. So, you continue with these, and that. Right. The result of a schedule will lead to an FSM that looks like this from the CDFG. That is the simplest way to generate a finite state machine, and you can see how the synthesis process will proceed. Okay. So, this example here will translate to what FSM? I have to look at what are the operations that are happening there. We have to actually schedule that the individual basic blocks, and in any case, when you have an if statement, you have a fork in the FSM. You have multiple paths starting from the same node in the FSM, same state. But can we do something about this? It seems as though it is too expensive a hardware translation, considering that our if statement was so simple. If I did not do all of this, if I did not do behavioral synthesis at all, and this was there in my SDL, just that statement was there in the SDL, what would be the hardware that that translates to? You have a mux structure in which what are the inputs, what are the output?
Selection lines are x is the selection.
That is just x. Of course, the x equal to 0 simplifies this. If this was a more complex expression, then that complex expression would be evaluated, and the result of that anyway is a Boolean result, and that is what would go into the select signal. The output is y.
A plus b and a minus b will
Right. So, I have it says minus that kind of a structure, right. This sort of a structure would be the hardware that is inferenced. Could we inference such a thing given our methodology for high level synthesis? Actually, the mux was not introduced as one of those data path components. This is inferred from the fact that there is a sharing somewhere, or in this case actually it is not because there is a sharing, but it is just that the different control paths are there and different computations happen in those control paths. However, anticipating a hardware like this, we can do some at least local transformations that take a control flow graph and generate a data flow graph from it. So, that is what the original CDFG was. What we are saying is this is so simple that why do not I just create that data path element, that mux there. Right now, even though we haven't gone to the later resource allocation and sharing kind of steps yet. And I just translate this into a data flow graph by essentially throwing out the if statement completely, but transforming that into a mux component or a mux functionality. So, it actually becomes a node in the data flow graph with the functionality being that of a mux. Yeah.
Sorry, wouldn't it be preferable to have an additional work mux for the fork step so that you don't end up computing both plus and minus simultaneously? You compute only on plus or minus as necessary. Basically, I do not know how to do it in DFG. In CFG, that is what we were doing. We were computing only one. But here, we are saying
this kind of a transformation leads to some redundancy in the evaluation. Whether it is needed or not, whether hardware is duplicated or not is not clear. Yes. This is only a DFG as of now. You could schedule the DFG in the following way. That could be scheduled in one. This, for example, could be scheduled in a different cycle if we wanted to. Remember, the hardware from this is not obvious yet. It is possible that we can share both of these on the same function unit like an ALU if we wanted to. Yeah, that kind of a hardware is of course meaningful. It does mean a little bit of an extension of our abstraction. Now, I should have a multi-function unit that is capable of doing both the plus and the minus. If you have an adder and a subtractor anyway, and you want only the addition to be performed or the subtraction to be performed, then you could still do that, but then well you need some control signal there that tells whether to activate or not. Normally, we assume that the adder is just a simple combinational adder that does not take any such control signal.
average power may not be impacted, but still there will be additional power spent.
Yeah, since you are doing some redundant work, there is additional energy spent. Average power is impacted, not in this schedule, but if our schedule was this, right, then it is impacted because we are doing more work in the same cycle. Total energy is impacted because you are doing more work, and therefore that must show up in more energy ultimately. Yeah. But this does avoid the need for splitting the FSM into multiple parts and joining, particularly when the statements are so simple. If they are complex, then it is usually worth it, but if it is something like just one state each, then it may be worth considering transformations like that. This should also illustrate the general mechanism for how to handle if statements in synthesis. Right. If I have an if statement, that is my condition, and I have a bunch of assignments in one branch of the if, and in the other branch of the if I have another bunch of statements, and so on. What does the synthesized hardware look like? Just translate this into hardware without necessarily going through the behavioral synthesis steps. So, the presence of an if leads to the creation of a mux. Now, what kind of mux it is, and what do we have at the inputs and outputs of the mux? Let us call these let us say P1, P2, P3, P4, so that they represent some expressions that are being evaluated. But we want to see the impact of these assignments. How do we translate these assignments into
Multiple muxes will be there for every
multiple muxes? We need a mux for
every assignment.
every assignment.
Like for if A variable and B and C, 3 are there.
Yes. For every variable that is being assigned, distinct variable that is being assigned, we need a mux. Yeah. So, that is what I would need. So, for A, I would structure it like this. right. So, these are muxes, and P1 and P3 are computed separately, and one or the other goes into A. There is the question that what do we do about the fact that there is redundancy here. We should be evaluating either P1 or P3, but if you create hardware like that, then you are evaluating both P1 and P3. But this is a standard delay versus maybe power trade off. This does mean more power because you are evaluating both of them. From a delay point of view, it is okay, you are finally selecting it. So, that select signal is the same, right, in both the cases, all the cases. What about the B?
Goes to self and
B is assigned,
then feedback.
the other one? The assumption, of course, if you leave out in one of the branches, leave the assignment to B out in one of the branches, then it should retain its old value, right. So, that naturally leads to a memory element being inferenced, right. You can't directly connect this, but essentially it may be that in our context we create a memory element register, latch, whatever it is, and connect that back. For C it would be similar.
Sir, if we are using a latch, then do we require a clock also for?
That depends on the methodology. In fact, a latch implementation may be like this only, right. If there is no clock, then that is how the latch would be implemented. No, the moment you put that feedback, it is no longer a combinational circuit. Yeah. You can see these are some of the early errors that you might identify when you write some VSDL and you try to synthesize it. The tool reports memory elements, latches are inferred, whereas you did not intend any. So this is just a if statement, where did I create the memory element. It is inferenced because of this imbalance in the assignment statement. In one branch I have an assignment statement, in the other branch I do not have an assignment to that same variable, then I am implying that you remember what the value of the variable was earlier. That leads to a latch kind of functionality. Same happens if you have case statements in which
Explicitly in the else block, if we explicitly declare in the if block we are saying A equal to, let's say, B,
yeah,
and in the else block we say A equal to A, then will also a latch will be
Yes.
else if you say A equal to A, that is fine, but the way to get around this, the way to still realize a combinational circuit from here is of course to make sure that A is assigned something earlier, let us say as is initialized to a constant, right. If you initialize it to something, then it does not matter, whatever that value was, that is the one that would go here, that is the one that you would connect to this, because in one path you have overridden that value, in the other path you have not overridden that value. To B you have make it B. So, in this path you want B to take the value of P2, in the other path you want B to take the value of 0. So, the mux structure is actually fine.
Constant just before if.
Yeah, so that is the value that reaches this if statement, if that is clear. So, then we could just have whatever that value was, we could add it to the mux, and that may help us avoid the latch in the general case.
So generally the tools don't allow the use of if without a process. Like for example,
without a process, yeah, if these are statements that would go inside a process, yes. Yeah, if statement is there only inside a process. Yeah.
So that default value that you are saying, it should be assigned outside that process.
Outside the if, within the process, but outside the if.
Outside the if.
Right.
Okay, so whenever. Okay.
Yeah, so these multiple paths here through the then and through the else is what caused the inference of the mux, but the absence of an assignment in one of the paths caused the memory to be inferenced. But if you are sure that it is a combinational circuit that you have in mind, then whatever the assignment is, it could be a more complex function, but that function goes as the other input to the mux, and there is no need for the feedback to be introduced in the mux. This is an important thing to remember as you try to work with some synthesis tool, RTL synthesis tool. The way to write your RTL such that combinational logic is inferenced even in the presence of conditional structures like this is to make sure that every path that assigns something to this is a known path. You do not rely on remembering the previous value. So, this whole thing could be inside a process and it is fine. We do not rely on remembering the value of B from the previous triggering of the process. Everything is still determined from this triggering, which is this function is computed, right. It is assignment or it is a more complex function. It is computed right there. That would lead to a combinational logic. If you rely on remembering the value of B from the last time the process was invoked, then you need a memory element.
Sir, if we have some single assignments in the if block and in the else block we simply say that wait until clock pulse, then latches will be created.
Wait until, if you have wait until at random places, then memory is inference. There is no way around it. In fact, RTL synthesis tools will not allow you to put wait at random places. They will take the weight, but then they will restrict where you can place the weight. Maybe it is at the top or at the bottom, or you do not have a weight, but have only a sensitivity list, then it is okay.
They say that ignoring this statement. That
Yeah, but ignoring is at your own risk, right? Right. Because they do not have the flexibility to insert additional cycles. Flow graph flattening is a more general mechanism. Having flattened that if statement, having converted that representation from a control flow into a data flow. So, essentially this part got transformed to this, right. Now, this could be a nested if statement. You can recursively do this flattening at higher levels also. Of course, this should be carefully done. Normally, we would do it if those basic blocks S1, S2, let us say they were simple enough that the logic that is resulting in the CFG to DFG transformation is also simple. At some point, if you arbitrarily do it irrespective of the nesting level of the conditions, the graph might just blow up in complexity and you might not want to do
What
that.
kind of thresholds are used to demarcate this decision?
Well, the simple threshold could be that you constrain the width of the mux. Up to 2 inputs is okay, but if it becomes 4 or large, then you do not allow that. So, some such simple heuristics could be used. Other thing is that this leads to a larger number of evaluations, larger number of operations being evaluated, like we had identified earlier. More and more redundancy is introduced, because if you have 8 paths, only one of them is being taken, you would be evaluating all the 8 operations. So, you could actually restrict this to the number of levels that you do this over. Indirectly, it would also be the number of inputs to the muxes. Okay. There are rules from Boolean logic that could be used to simplify parts of our expressions. So, if there is some function that I have here, which may be applied to bit vectors as opposed to bits. If it is simple bits, then it is all right. It will get optimized at some stage when you do logic synthesis, it might optimize it out. But some of those rules of Boolean logic, particularly the ones that extend to bit vectors as opposed to just bits, those one can run some paths to perform some simplifications. Idea being that these are very simple operations, even though they may be operating on large bit width data. Since these are bitwise operations, the time taken will be small, and there may not be a need to explicitly schedule these kind of operations, considering that you also have those kind of operations being scheduled that are going to dominate the clock periods anyway. some kind of pattern matching can be done based on what kind of resources we have in our library. Those would be like this. Say you have C equals AB plus C. This is an multiply accumulate function. One could actually simplify this into a MAC operation. This would make sense if such a MAC unit was there. So, that unit, if it is there explicitly in the library, is likely to be more efficient than a multiplication followed by an addition. It is hand optimized to do that. So, such a substitution, if we would like to exploit that particular unit, so essentially pointing to the fact that the same graph may be translated into many different kinds of hardware. So, alternatives are there. Multiplier we do have, adder we do have, and a MAC unit we also have. And the knowledge that the MAC area, for example, is lower than the multiplier's area plus the additional area, or the same thing with the delays. We could use that during this pre-processing step. Later on, if I do the scheduling on that graph there, then it is hard to exploit the presence of that operator in any way. Since they are individual operators, I have my multiplication, I have my adder, but early on it might actually be an opportunity for me to replace a subgraph, a more complex subgraph, by a single node, knowing the functionality of that more complex library operator. Those pre-processing steps being done, let us go ahead and discuss some of the core high level synthesis algorithms. So, the first step, of course, we had identified was scheduling. The point of scheduling is to take us a little closer to the hardware domain, as opposed to that CDFG, which of course is purely functional in nature. There is no timing related information there. Closer to hardware means that first let us introduce some timing partitions, and the result of scheduling visually is just this. These partitions are identified. This is an important change in abstraction of that representation, because we are saying that not only is this the functionality, but also we are saying that these two operations will be done in the first cycle, this one will be done in the second cycle, this will be done in the third cycle. That is essentially what takes us down from the behavioral level of abstraction into a more concrete register transfer level of abstraction, because we are explicitly saying what should happen when. Everything is still not decided, specifically which hardware unit is going to perform which operation, that is not clear, but we have at least made the decision that these two operations will be performed in the same clock cycle. That is still a major step taken towards the implementation. This of course is a key step in going from an abstract to the clock domain. The idea of a clock was introduced only here, right. Until then there was no idea of a clock. This is a classical problem. Scheduling, as you can imagine, this is a synthesis manifestation, but overall the scheduling is a general problem that applies in many different contexts. In all of those, let us say the application could be airline scheduling or job scheduling on a multiprocessor and so on, a very large number of applications. All of them would have something in common with respect to the representation of that problem in the form of a graph. That is generally how it is represented, in the form of dependencies, tasks, dependencies between the tasks, and any constraint or deadline that you might impose within which the scheduling algorithm should work. Let us introduce the formalism here by capturing our design in the form of a graph and ask questions regarding what the scheduler should do subject to what constraints we are imposing on it. So, this is a known NP complete problem. It is difficult to solve optimally, which just means that an exact polynomial time algorithm might not exist. However, since it is a practical problem, it means that we still need a solution, even though we are not making guarantees about its properties. So, that brings us to the domain of heuristics. From an engineering simplicity point of view, one can try out several different heuristics. They may have different complexities with respect to time, and an appropriate one has to be chosen based on several different situations like the size of the graph and so on. But it is an important problem. Generically, one can formulate the scheduling problem in many different ways. One could be a resource constrained scheduling, which means that resources are given, you have to generate a design within those resources. Of course, that CDFG is given. What we are scheduling here is actually just a data flow graph, not even the overall CDFG. We did say that the way we will handle the CDFG is we will schedule the data flow graphs individually, one at a time. So, it is just a data flow graph that is given. It is a DAG, no cycles even, but that does not make the problem any easier. So, resources are given, you determine the minimum delay schedule considering the DFG is given, resources are given, the latencies are given of all of those operations. Right. So, those operations have to be mapped to the resources. So, the resource library consists of elements whose delays we should know, whose area also we should know, but we are saying that in this form we will define the resources, fix the resources, and you say that use these resources and give me the minimum possible delay schedule. That is one way to formulate the problem. You could also go the other way around. You do not fix the resources, but you fix the time. In one, you fix the resources and ask it to generate the minimum delay schedule. You could also say that the delay is fixed, the deadline is provided, and within that you just generate the minimum resource schedule. Which one to take, that depends on the design scenario. It depends on what the constraints are and what you are trying to optimize. If the constraint is that you need a solution that must fit within a certain area, then you might go for the first version where resources are constrained, and the objective of scheduling is to just minimize the delay to the extent possible. It could also be that your application is such that the result must be generated within a certain amount of time. Okay, that is part of the functionality we might consider it. So, then we will just fix the time, and the objective of the optimization then is to minimize the resources. Both are difficult problems, it is just which one is applicable depends on the design scenario. So, we will first look at the version where we make a lot of simplifying assumptions. First of all, there are no conditionals, we are scheduling only within a basic block. But of course, we know how to extend that solution into multiple basic blocks. So, at least a simple way to do it is you schedule each of the basic blocks separately. So, that is fine, there are no conditionals, and therefore, we are not talking about a CDFG to be scheduled, although we will relax that later on, but that is the assumption that first we start with just a basic block, which means just one DFG needs to be processed. Let us assume that all the operations take one cycle. That is just to simplify the presentation of the algorithm, it does not make any difference. The problem is still difficult even if you assume that all operations take one cycle. And let us assume that there are single function FUs, meaning that you do not have ALU kind of functions that are capable of performing both an addition and subtraction and a bunch of operations. We can easily relax all of these constraints later on. Once we define the basic strategy, we can relax this one certainly into multi-cycle operations. It is a simple extension. We can have chaining of operations into the same cycle, means that there is one operation dependent on another operation, right. Both of them could be scheduled into the same clock cycle if enough time was there. You could have multi-function units, you could have ALUs that are capable of performing more than one operation type, you could have conditionals and so on. All of these are generalizations that take us in different directions, but just to simplify the algorithm, let us just make these assumptions for now. There are a large number of possible heuristics to solve scheduling, knowing that an optimal solution is not easy. You do need a solution soon. It is the kind of problem where you can't afford to spend too much time, because the algorithm is applied possibly on a graph that has a very large number of operations. So, the solution should be scalable in the sense that if you have thousands or tens of thousands of operations in your process, then too we should be able to come up with a reasonable quality solution. So, the algorithm that we will look at is one variation of a number of different strategies you could take to perform scheduling, but this is chosen because it illustrates several principles along the way. That leads to first a computation of an as soon as possible schedule and an as late as possible schedule, that is the ASAP and the ALAP. This is not the final scheduling strategy, but they are useful nevertheless, because they result in some bounds, an upper bound and the lower bounds for what is the earliest that a particular operation can be scheduled at and what is the latest a particular operation can be scheduled at without violating deadlines and so on. Okay. So, let us define the terminology in terms of which we will present the solution. So, that is my DFG. As you can see, the application here is the scheduling context of high level synthesis, where these operations are our arithmetic kind of operations, plus, minus and so on. And what do these edges represent in the graph? They represent precedence or dependency. Right. The V node can be scheduled only after the U node is completed, because it is using the result that is computed in U. You can see that this is a very generic representation of this problem statement. The representation would be the same even if you change that level of abstraction completely, and because of which the problem statement might completely be different. Let us say this becomes a task graph in a multiprocessor context. U, V, these are not simple operations, but each is a program. This is a task to be scheduled, and program U is producing some data that V is dependent upon, and scheduling's representation still does not change. This graph is still the input to the scheduler. It is just that each is associated with a delay, right? X has a delay, V has a delay and so on. There is a latency that is associated with each of those. Those would change, and of course, what U is doing, what X is doing, these are not the business of the scheduler's strategy. The scheduler just needs to know the dependency structure which is captured in the graph. It also needs to know the latency of these operations U, V, how long each of them takes, so that the appropriate schedule can be generated. You can see that if this were multiprocessor task scheduling, the formulation would still be the same, and your solution might actually still apply there. Of course, the meaning of the tasks is different, the meaning of the resources would also be different. Here our resources are ALUs and multipliers and so on. There, what would the resources be? In a multiprocessor task scheduling, the task would be a program, resource would be what? The processor. Well, it could be lots of things, but essentially you have a set of CPUs and their associated memory hierarchy and so on, but you have to take a decision of out of all the tasks that are there in this flow graph, which ones should be mapped to which processor at which time. So, it is the similar problem. You could cast many other scheduling kind of problems according to the formalism like this, where you just capture it in the form of a graph where a node represents the computation, but really we have made no assumption about what kind of computation it is. It could be very simple, it could also be a complex. But the edge represents dependency, which means that if there is an edge from U to V, then V is ready to be scheduled only after U is complete. Okay. So, that is our set of nodes in the graph. Edges represent precedence or dependencies. I say if there is an edge from U to V, then U is an immediate predecessor of V, and V is an immediate successor of U. Why immediate? This is as opposed to the relationship between X and Y, where X is a predecessor of y, but not an immediate predecessor because there is no direct edge from x to y. I can define this set pred of y to be the set of immediate predecessors of a node y. Here that would be these two nodes, because they have outgoing edges that land at y. Same thing with successor set, that is the set of immediate successors of a node u. So, for that node the set of successors are these two, immediate successors are these two. With that we should be able to come up with a simple ASAP scheduling algorithm. That algorithm might look something like this. The idea could be the following. That is our DFG for ASAP scheduling. Assume that there are an infinite number of resources. If that is the case, what is the earliest that a particular node could be scheduled? How do you find this out? Let us answer this question of which nodes could be scheduled in the first clock cycle. All of the nodes that do not have any incoming edges, because they do not depend on anything, we can collect all of them and schedule them into the first clock cycle. That should lead to an obvious strategy for how to do ASAP. After identifying these nodes, how do you continue with ASAP? Yeah, just remove those nodes from consideration and apply the same strategy once more, right. So, that strategy should be simple. We could write variations of these algorithms, but essentially it could be that I first pick up the first cycle in this way for all the nodes with no predecessor, no immediate predecessor. I just schedule. So, the sigma is just the schedule number, it is the clock cycle value that we are assigning to a particular operation u. So, sigma of u is 1 means that all of them are going into the first clock cycle. Then I just, so having considered u already, I remove u from the set of nodes under consideration. Fine. After that, all I need to do is iterate through the remaining nodes. We have already deleted a bunch of nodes from that set V. For all the remaining nodes, let me just iterate through and make the following check, that I will check whether all its predecessors, immediate predecessors, have been scheduled or not. How do I know? Of course, I initialize that schedule to something else, a negative number or something like that. If it is assigned some positive number like 1 or anything else, then I will say that if all the predecessors of u are scheduled, then the u itself is ready to be scheduled, right. And I can assign to u a clock cycle which is what? I have said 1 plus the max of the schedule value of all its predecessors, saying that if u is dependent on a number of nodes, right. So, that is one, that is one. Each of all of these guys have been scheduled already, then we are just saying that it is 1 plus whatever is the max. What is the reason for this?
The last schedule is in third cycle,
Right.
value will be available after third cycle,
Yes.
schedule in the next cycle.
All its predecessors might not have been scheduled in the same clock cycle, they might have been scheduled in different clock cycles. So, the earliest that you can schedule u is the cycle after whatever is the latest that any of its predecessors have been scheduled. Yeah.
Sir, why did we have to do a separate block of statements for the first one? When the initial source nodes of the graph, we wrote some specific lines and then we are using this algorithm. Why isn't this valid at the first point itself?
It is not valid simply because, well, if you use this computation 1 plus max of the predecessors, what does it mean? If you do not have a predecessor, you have to appropriately define it, that is all. You could write the whole thing in one loop, taking that into the initial condition also as part of that computation. Okay. So, with this you are not necessarily identifying the nodes one level at a time, but you would get a result which is the same. What we are doing is, so let us say the first level has been identified. Then I moved on to that node, all its predecessors have been identified. So, that is all right, I can assign a node a cycle to this. Following that, let us say I came here. Actually, I did not say anything about the order in which you traverse that loop. I just said for all u belongs to V, and actually you can see there could be an efficiency issue in the order in which you follow. Right. So, yeah, you may need to revisit that or refine that according to some of the other logic, remember that we have already looked at, but it does mean that there are multiple orders, and the number of iterations that you would go through might actually depend on the order in which you are looking at it, although the result will not change. So, if I look at this one next after this, then I am at a situation where all its predecessors have already been scheduled. So, I can derive the schedule for 3, even though this one is not yet done, this would go into the second cycle, but I picked this node to process next, and so I should be able to just find the schedule for that, and then that leaves this, and that can be handled by just noticing that its predecessor has been scheduled, and the earliest that we can schedule this is 2. That is my ASAP schedule. Correspondingly, we can do an ALAP schedule. The idea is analogous, but we are trying to find out the latest that you can schedule any node. Given the same graph, what is the latest that we can schedule any node? The strategy somehow would be similar, but we go in the reverse direction. But how does one go about it? The earlier algorithm was that we looked for nodes with no incoming edges. If we are looking at as late as possible, how do I go about it?
With no outgoing edges.
We can start with nodes that have no outgoing edges, but where do you schedule it? ASAP was clear, you schedule those nodes that did not have dependencies into the first cycle. For ALAP?
So, the timing constraint that is given.
ALAP needs a constraint, right? Otherwise you could postpone it forever, and therefore it has to operate with a time constraint. So, this time constraint, let us just impose the third cycle as the timing constraint, which means that the deadline for performing this is 3. Where did 3 come from? Maybe we first did an ASAP and then realized that the length is 3. ASAP found a schedule with 3. So, it certainly means that you can't find a schedule that is shorter than 3. Right. Are you convinced that if ASAP gives a number for the number of cycles that it took, it is not possible to find a shorter schedule? Of course, it had better be, if we are saying it is, the name itself says as soon as possible, you should be able to prove that you can't find a shorter schedule than that. We can take that, of course, it need not be 3, it can't be less than 3, but it could be 10. But if it is 10 as opposed to 3, what happens to the resulting schedule? Maybe we answer this question later on. Let us go ahead and solve this. I identify the nodes with no successors and assign them to the last, whatever is the deadline, we assign it to there. Then
We delete that.
those nodes are removed, and also the cycle is decremented, and then so the deadline is updated, and then I again run the same thing. So, this is similar. So, I identify which are the nodes that would go here. So, that node has its dependency stated. So, these 3 nodes are selected, and let us say into the second cycle, and the other 2 nodes are selected into the first cycle. We went in reverse order. The algorithm would also be very similar. That initialization step would now be applied on the nodes that have no immediate successors, and that T is what is specified there as the cycle into which we are scheduling it. Removing those set of nodes from consideration, then I run through the same logic, but for all of those remaining nodes, what we are checking is if all these successors are already scheduled, then that is the logic. Does that make sense? You take the minimum of the clock cycles into which we have scheduled all its successors and subtract 1 from it. You see, this is the reverse logic, right, and you remove that node from consideration and continue in the loop. Both of these are relatively straightforward. These are not difficult, right. This is the extreme where the assumption was that there is no resource constraint. So, obviously, this is just an ideal schedule. It does tell us something though. Some valuable information could be inferred by just doing an infinite resource scheduling like the ASAP and ALAP where even in the context where resources might be constrained in some way. What information can we derive from here? These are ideal schedules, remember, they made assumptions that were violating our constraints in terms of availability of resources. But still, what information could be derived from here that is useful?
You are scheduling in DFG in a particular cycle, where can you schedule first cycle or third cycle?
Yes, it bounds for us the range in which the schedules of individual nodes can lie.
Why should I give 3? I can even give 0, I'll get negative number, then I can offset it back. I mean, I need not give any number.
Yes,
So
we will look at why we are doing it this way. There is a reason. If you were to do just ALAP scheduling, then you do not need the cycle, but with what we are going to do with this result, you do need a constraint. Right.
If I am taking my entire FSM in one go, I can always offset it back to the latest.
Yeah, but
item.
why don't we look at what we are doing with this information. So, let us compare the ASAP and the ALAP schedules. ASAP schedule looked like that, ALAP schedule looked like this. If you compare, you will find that there are some nodes for which both the ASAP and ALAP schedules are the same. For this set of nodes, they are the same. But there are other bunch of nodes for which they are different, and here is one inference you can make, that these are nodes for which the schedule is fixed, irrespective of whether it is ASAP or ALAP, are the nodes that we will say fall in the critical path. Right. But there are these other nodes for which it seems as though there is some flexibility. Even if the deadline was 3, then W I do have the choice of scheduling into the first cycle or the second cycle. X and S are also similar. All of those nodes are not necessarily as critical as the UVY Z, for example, is. That information is valuable information that could be used in a realistic scheduling algorithm. So, our bounds are these, right. For U, V, Y and Z, these are the nodes that were critical, and for these in fact the schedule is fixed. Right. But for these other nodes we have defined the ranges. As of now we have not made the decision. I do not know the resource constraint yet, but even without the resource constraint we have classified the nodes into nodes that are in some ways more urgent to schedule or more critical versus those that are less critical. That kind of information is inferred from the ASAP and the ALAP schedules, even though they have made assumptions which may be unrealistic, but still these are properties of the graph, and that information that is derived from here could be used in some ways by us. How we will use it we will just get to, but let us keep in mind that we have already done that kind of analysis. That is simple to do, both the ASAP and the ALAP. How simple is it? Let us get back to that algorithm here. Yeah. What would be the complexity of that ALAP scheduling algorithm, as also the ASAP scheduling algorithm? It is the same. Let us go to the ASAP instead. Right. How about that initialization step? How much time does it take?
So we are traversing every vertex to find out if it is a source or not.
This is a loop, right? The body is a constant amount of work that is happening in the loop. So, somehow everything is happening here. How much work is happening there? For all the nodes for which the set of immediate predecessors is null. To do that, you have to go through all the nodes. For each of those nodes, how much work do you need to do? All the incoming edges have to be identified. You can see the what is the worst case. So, worst case complexity just for that initialization.
V plus E, order of V plus E.
Order of V plus E. Why?
So I can have a straight chain.
Yeah. Let us say to simplify this, let us just make it on the of the order of if there are n nodes, then what is the complexity? Worst case for that initialization. Order of n, and one node u can have how many predecessors? That is my, let us say the u was here.
N minus 1 predecessors.
It could have all of these guys can be, we are looking at the worst case example, right. So, in fact, you could have n predecessors, the worst case you can have. What about this node? The directed edges, of course, that one could have how many predecessors? It could have. So, what is the complexity just of that initialization? N square, because for this I have n, for this maybe there are n minus 1 and so on, 1 plus 2 plus up to n and so on. So, that could be an n square complexity. In the worst case, of course, realistic graphs may not look that way. Yeah.
Sir, we are not looking for all the incoming edges, we are just looking for the nodes which have no incoming edge. We are
Right.
looking for the one which has no predecessor, right?
Yeah.
So, we need not go to n minus 1 times the same body. We just need
Well, this is a good point. It depends on how you have represented it. How do you represent the graph?
Sir, I don't know how do I present the graph as in like we have a simple graph.
Here is a representation, node 1, node 2, node 3 and so on, 1, 2, 3, right. Each element here tells whether there is an edge from 2 to 3, right. That element says whether there is an edge from 3 to 2 and so on. If it is a matrix representation, then finding that you have even one predecessor or not does require a traversal in the worst case. If it is a list representation, it can be better than that. Yeah, you just need to know whether the list is empty or not.
So,
In
in
fact.
that case, we will have order of n only, because then for everyone we just have to find out if it has a successor or not.
Yeah,
So,
you could do that.
order of n simply.
Right. What about the next part? This part. Let us get to the body itself. How much time for this? Just the worst case. 1 plus, so this is simple, this part is simple. What about the max? Max of all predecessors would involve traversing all the predecessors. So, how many predecessors can I have? I can have n predecessors. So, this max, the loop body itself actually might take order n time.
Yes, and we are doing that for every vertex. So, n square हो जाएगा.
Here too you can try constructing the worst case. The body takes n. I have taken node u and I am checking if all the predecessors have already been scheduled. Actually, that even though we have written it in this way, the max can be computed simultaneously with the traversal of all the predecessors, right. Otherwise, if you arrive at the loop body and then perform the max by traversing the predecessors again, then it seems as though you are doing extra work. But essentially all of these guys and all of that computation could be done together Yeah. So, if you find that one of those nodes is not scheduled, then it is all right, you have to abort the process and then just go to the next node. Right. So, let us say order n work is done for this. Now, getting here, for that loop you are going through all the nodes, well maybe all the not all the nodes, but remember you are removing nodes as and when you are processing it. So, that the number of nodes you are processing could actually reduce as you are going through the loop. So, how much time for this? This you could actually be going through n nodes in the worst case, and that means that this itself is n square as of now, because this was n, that could be n square, but everything is not resolving in one iteration of that outer while loop. Depending on your example, your worst case might actually lead to only one node being resolved in every iteration of that inner loop, which leads to an n cube kind of complexity. You can try and construct a data flow graph for which it is actually the worst case, but we should understand where all the complexity comes from. What we have done so far, this is a pre-processing. We just did the easy thing first, which is doing an ASAP schedule and an ALAP schedule, and the objective of doing that was that it revealed to us what was the range we really have, or in some ways it prioritized the nodes for us. Some of the nodes are more important to schedule, because if you delay some of the nodes, for example in the critical path, as you do the actual schedule, then all its subsequent nodes would get delayed. On the other hand, if you delay some node that is off the critical path, right, for which it seems as though some range was there, then you do not necessarily immediately incur a cost. Maybe it can be adjusted later on because some flexibility was there. Some nodes it is more flexible, other nodes are less flexible. That is what is the basic information that one derives from the ASAP and the ALAP. If you do both of them and you subtract one from the other, if it seems that that number is not 0, then there is some slack. If it is 0, then you have less slack. Anyway, let me stop here.